right, it looks like we are slowly reaching steady state. Okay, welcome everyone. Welcome to the RC Flex from Space webinar series. Today, we're gonna hear from Ernesto Rodriguez, who's gonna be talking about some exciting observations from airborne instruments. Take it away, Ernesto.
Hi, everybody, and thanks for joining. So, as Via said, I'm going to be talking about some results from the S-mode experiment. S-mode is a NASA Earth Ventures suborbital mission that has been going on now for close to 5 years, I guess, given COVID. But we had 3 missions, or 3 large-scale deployments in 2021, 22, and 23, during which we collected data over the California current west of San Francisco with a very wide array of sensors. So we had both shipborne sensors, some autonomous sensors, both at depth and at the surface, and also what I'm going to be talking about mostly is a sensor called Doppler-Scat, which is a NASA instrument built by JPL that flew together with a sensor from UCLA called MOSIS that got SST. So I want to thank the S-mode team. We've been working together now for many years, and we've had very successful data collections, and now we're all busy trying to make sense of the data. So hopefully this is going to be one of the many talks that you'll be hearing about exciting results that's coming out from S-mode. Specifically, we're going to be talking about an instrument called Doppler-Scat, which is an instrument built by JPL that measures surface currents and surface winds simultaneously using a Doppler scatterometry. What's new relative to regular scatterometry that measures surface winds is the ability to measure surface currents using Doppler. And because we're flying fairly close to the ground, 30,000 feet, we have 200-meter resolution, which is much better than we would do from space. And so that opens up a lot of exciting possibilities about measuring things at the sub-mesoscales and taking a look at what could be done from future missions from space. On any given day, this instrument will collect a wide strip. Each strip is about 100 kilometers by 40 kilometers, and we usually stitch those strips together to get something which is on the order of 100 kilometers by 100 kilometers or so, and get synoptic coverage over one day. I want to say that all these data collected under the EVS-3 are in the public domain, and if you want to play with it, then please do. They're available in NASA PODAC. So please feel welcome and feel free to ask me any questions you want in terms of usage of the data and any hints that you may want to do it. Okay, so the topic for today is the modulation of the wind by the ocean and vice versa. It's been known for a really long time. Dudley Shelton and company in 2004 took a look at QuickScat data that SST fronts have a deep impact on surface winds and surface stress. Ernesto in 2016 and subsequent publications and others as well have been also making the point that because you're sensitive to surface stress, and stress is relative to the moving ocean, the surface stress will be modulated by the currents. And that has implications both in terms of how the winds kill mesoscale motion, but also how the ocean currents influence the winds above them. So there have been both experimental studies using spaceborne scatterometers and geostrophic currents And recently, modeling studies at higher resolution, because the scatterometers can only get on the order of hundreds of kilometers because of the geostrophic current resolution. So to go to smaller resolutions, they've been modeled. And I like to point out recent results by Runabai and Conejero that looked at both SST and currents. So the questions that I'm going to talk about here today is, does this coupling depend on the spatial scale for real data, right, as opposed to modeling data? Does the coupling depend on the atmospheric stability conditions? And do curls and divergences couple in the same way? One of the things that I'm not going to address here, but it's also being worked, is the SST coupling from S-mode. Since I'm not going to address it, I'm going to show you something to make you yearn for this data. These are results that Alex Weintier shared with me recently of work he's doing for the thermal modulation. And we have on the left are winds measured by Doppler scat over a front, a thermal front. And on the right is the high resolution SST measured by the UCLA MOSES instrument. And you can see the obvious influence of SST on the winds. But I'm not going to say anything else about it, except that you'll be able to see these modulations at hundreds of meter scales. And so these data set are very rich. But here I'm going to be concentrating on the modulation of the winds by the currents. And so the basic mechanism is fairly simple. If you have in this case, an anticyclonic eddy, and you have winds blowing from the top, if you look at the stress, you have no current feedback on either side of that eddy, you would have the same level of stress. But because the stress is relative to the moving surface, what you actually have due to the current feedback is something more like what's on the right, where when the wind is blowing against the current, the stress is enhanced, whereas when the wind is blowing with the current, the stress is decreased. And so that has modulation effects both on the forcing of the eddy killing, on the wind work, and so forth. There's a secondary effect that also comes in, and that's what's seen in the lower panel, is that because the stress is lower on when the wind is blowing with the currents, the feedback on the atmosphere is also lower, and so there's less deceleration in the atmosphere. So it's an acceleration relative to the currents, relative to you would see if just you have the surface stress being the dominant mechanism. So here are some of the modeling results that Renaud and his coworkers have gotten. So what you have in the left, on the lower left, is a plot of the conditional distribution of wind stress curl on the y-axis, as opposed to relative vorticity on the x-axis, the ocean current relative vorticity. And what you see is that they're anti-correlated with a certain slope in that correlation, which is what Leonello and company called the coupling coefficient. And so one of the things that we're going to be looking at is the nature of that coupling coefficient from real data. If you look not at the wind stress, but if you look at the wind curl, the atmospheric wind curl from the model, and bin it again the relative vorticity from the ocean, what you see is that the coupling changes sign, at least in this study, and it's correlated, showing this increased acceleration. So an anticyclonic ocean eddy would have an anticyclonic wind eddy on top of it at above above the surface. Some additional work that's been going on recently, Lunabai and company took a look at additional modeling in the Southern Ocean. And what they did is characterize this coupling coefficient as a function of wind speed. And so here on the lower right corner, you have the coupling coefficient as a function of wind speed. So it's negative and is decreasing as a function of wind speed. And so we'll examine whether that holds for the data set collected during S mode. The other thing that we can take a look at with S mode is have a hint about the stability conditions of the atmosphere. And to do that, we build on some of the recent results by Stopa et al. And Driscoll et al. That take a look at the texture of the winds and relate that to the surface layer stratification or Richardson number or the Bukov length. So what we've done is we've done a classification of the winds that we observe, and you can see some examples on the left. And purely by eye classification, not using the machine learning results from these two papers, because there is no training data set to use machine learning at very extremely high resolution and for the data sets that we have. So typical examples of what the type of stability conditions that we see during the S mode deployments, going from left to right, are wind rolls that occur when you have stable conditions and very high winds. So typically these occur when you have winds between 9 to 12 meters per second in the cases that we saw. And you see these modulations in the wind speed. So the wind is going along the direction of that arrow, and the modulations are in the crosswind directions. And so these are rolls in the atmosphere. And then lower down, what you see is the wind divergence and the wind curl. And you see these typical wind divergence and curl rolls signatures in the wind signature. Next, we have typical cells, and that's characterized by some sort of patchy divergence and curl without long wavelength structure. And those occur typically for middle wind speed, so on the order of 6 to 9 meters per second or something like that. And then when you have very low wind speeds, you really are able to see the filaments in the ocean. You have cases where the ocean currents are modulating the atmospheric winds, whereas in the roll case is the opposite. And you can see all of these filaments, we actually reflect filaments in the circulation, both in the divergence and in the curl. And so one of the things that we're going to be doing is stratifying our results in the coupling to see whether the texture or the stability conditions have any effect on the coupling coefficient. Okay, having said that, these are the Doppler data for the low wind case. And on the upper part, we have the relative vorticity from the currents, and then the wind stress curl. In both cases, they're scaled by F, even though dimensionally it doesn't make sense, just to get the numbers looking a little bit more in range. So you can think of it multiplying by 10 to the 4. And you can see the obvious anti-correlation feature by feature in between the relative vorticity and the wind stress curl. The same sort of correlation happens, or anti-correlation, although not quite as clear, happens in the divergence. So this is the current divergence and the wind stress divergence in here. And on the right-hand side, you see the histograms, the equivalent of these plots by Benoit et al. For the winds. So we have current relative vorticity over here, wind stress curl over here, current divergence here, wind stress divergence over here. The colors are the histograms, and then on the blue is the conditional distribution. And you can see the highly anticorrelated, like half point minus 0.46 correlation, and a coupling coefficient on the same order of magnitude as what was obtained by Renault and all in their modeling studies. And the other scale, on the other end of the scale, the high winds, these are examples for wind rolls. And you can see that in that case, you still have anticorrelation, especially in the divergence, although in the curl, it drops down significantly, as does the correlation. And so it's a hint that it may depend somewhat on the stratification. So let me just say that all these data were collected at 1 kilometer resolution. So one of the things that we can do is degrade the resolution of the data to examine the behavior of the coupling at different scales. But the other thing that we can do is, instead of looking at the neutral winds, which is what the scatterometers measure, we can take an estimate of the atmospheric winds. And recalling that the neutral wind is approximately, the atmospheric winds minus the current. There are some other additional terms when the situation is unstable, but this is a pretty good approximation. We can retrieve the atmospheric winds by taking a look at the neutral winds, adding back the ocean currents, and taking a look to see how those correlations look like. And so this is the first thing. Going back to the case of low winds at high kilometers, at 1 kilometer. And you see that unlike the results of Renault and all, the data are still anti-correlated. The correlation has dropped, but they're still anti-correlated when you look at 1 kilometer resolution. And when you look at the wind rolls, on the other hand, the sign of the correlation coefficient flips, similar to what Renault et al. Found, whereas the sign of the divergence for the atmospheric divergence still anti-correlated. So showing that the simple acceleration scenario where you have cyclonic and anticyclonic eddies on top of each other on the currents and the winds is not quite right, because of vertical circulation that happens due to the divergence. So this is a reflection of vertical fluxes that are happening. And so the coupling is slightly different between the curl and the divergence. But still, it's interesting that at this higher resolution, you're still anti-correlated in some cases and correlated in other cases. So one of the things that we wanted to take a look at is to see whether that correlation coefficient is a function of scale. And one of the things that we can do is degrade the resolution. So in here, I have examples that are 1 kilometer, 5 kilometer, and 10 kilometer. And on the left-hand panels, we have relative vorticity and atmospheric wind curls. And then on the right hand, you have divergence and atmospheric wind divergence. And you can see that in this case, the sign of the correlation for the wind curl is positive in all cases, and it's about the same as you change the scale. So basically, it's very similar slopes. But on the other hand, the correlation between the divergence and the atmospheric divergence changes significantly, showing that the vertical fluxes that are going on through the divergence terms are changing depending on the scale. So those were examples. If we take all the data that we collected under IOP1 and IOP2, which is our main data sets from the S mode, it's on the order of 60 days of data collection. And we've put all the stability conditions together. What we see here is relative vorticity versus wind stress curl as a function of scale. So the scales will be 1 kilometer, 2 kilometers, 3 kilometers, 5 kilometers, 7.5 kilometers, and 10 kilometers. And when you see relative vorticity versus wind stress curl, you see that the anti-correlation is independent of scale, in that case, showing that it's pretty much a kinematic relationship due to the fact that the wind stress curl is just responding to the relative current. And the magnitude doesn't change very much. If you look at the divergence, on the other hand, you see that it's also anti-correlated, but the strength of the correlation depends on the scale that you take a look at. And so that's showing the difference in vertical coupling at different scales in between the atmosphere and the ocean due to the divergence term. If you just take a look now at the atmospheric winds rather than wind stress, what you see is that the story is slightly different. For the relative vorticity, you have at the highest resolutions, you have anti-correlation, and then as you degrade the resolution, that coupling coefficient goes down, and eventually at the lowest resolutions on the order of 10 kilometers or 7.5 kilometers, you get the positive correlation that Renaud and Arnold observed before. So we see that, in fact, at the highest resolutions, this acceleration of the atmosphere is not really seen. It's only at the lower resolutions, when you're getting more to the scale of the boundary layer depth, that you're actually starting to see the acceleration of the atmosphere. On the other hand, for the divergence, for the atmospheric wind, you're anti-correlated the entire way, and showing that the nature of the coupling is significantly different due to, again, to the vertical component of the atmospheric ocean interfaces due to the divergence. The other thing that I want to bring your attention to is that all these distributions are essentially pretty much Gaussian. They're slightly skewed, but very much like a Gaussian, and that'll come back in a little bit. Now let's examine for a second the dependence on the stability conditions and the wind speed of this coupling coefficient. And so in the colors, I'm going to be color coding the stability condition, basically atmospheric rolls, filaments, what we call normal conditions, unstable and mixed, which are the basic classes that we were able to classify using I classification. And then on the x-axis, you have wind speed. And on the y-axis, you have the coupling coefficient. And then on the leftmost panels, you have curl coupling. Rightmost panels, you have divergence coupling. And then I subdivide that into wind stress coupling and atmospheric wind coupling. And so let's look first at the wind stress coupling, which is what's been published in the literature. So like compare against the results of Bai et al. Or the results of Renaud. We find anti-correlation and a dependence on the wind speed, with the wind stress, with the coupling coefficient getting stronger with wind speed, and getting even stronger as the wind speed gets very high, where you actually have a significant forcing of the currents by the wind. On the other hand, if you look at the atmospheric winds, the sign of the coupling changes, and there's no clear dependence on the wind speed or on the stability conditions. So sometimes you have cyclonic eddies on top of cyclonic current eddies. At other times, you don't have that. And this is at 1 kilometer resolution. If you look at the wind stress, what you see at the divergence now, what you see is that you have the same dependence on the wind speed, with the exception that the slope is increased by almost a factor of 2. And so we'll come back to that. And if you look at the coupling between the atmospheric wind and the divergence of the currents, it's a lot noisier, but you have a faint dependence on the wind speed, but largely anti-correlated. Let's take a look at what happens now as you change the scales. And so basically, the same plot as we had previously, but now 1 kilometer, 5 kilometer, and 10 kilometer. And what you see is for the wind stress, curl, and divergence, basically the story doesn't change very much. The correlation drops down and there's more scatter because basically you have fewer independent samples. On the other hand, for the atmospheric winds, what you have as the scale changes, you really start to see the coupling coefficients migrate from something around 0 with both positive and negative to something that starts to be mainly positive, and then at the lowest resolution, mainly positive. In that case, again, you have cyclonic eddies on top of cyclonic eddies in the ocean and the atmosphere. For the divergence, on the other hand, you don't see this switchback. You still have anti-correlation independent of the scales. So one of the puzzling things is how to explain this factor of 2 relationship between the divergence and the curl. So one of the things to take a look at is to see whether there's any changes, significant changes on the distribution of the PDFs between them. So going back to these PDFs, are the PDFs which are basically Gaussian, do the correlation coefficients change significantly between the classes? And do they change significantly with wind speed? And surprisingly enough, now we're dividing things slightly differently. So wind stress on the left 2 columns, atmospheric wind on the right columns, and then curl and divergence on each plot. You see that the correlation coefficient is negative for both curl and divergence, and it's about the same magnitude and about the same dependence on the wind speed. Slightly different dependence, but not that great a dependence. So the correlation coefficients are the same, but the coupling coefficients are different. On the other hand, for the atmospheric winds, there's a difference in the correlation coefficients where the curl is significantly lower correlation than the divergence. Again, showing that the vertical coupling between the atmospheric and the atmosphere and the ocean going on here. And so can we use the fact that we basically have very similar correlation coefficients to explain the differences in these slopes that have been observed in the various studies? So if you assume that things are basically Gaussian, you can actually derive the conditional distribution for the wind stress curl and the wind stress divergence as a function of current, relative vorticity, or divergence. And it's basically a function of the correlation coefficient, which we saw didn't change very much, and the ratio between the standard deviations of the wind stress curl or the wind stress divergence and the surface current, relative vorticity, standard deviation, or the surface divergence, standard deviation. So we know that for the ocean, the surface divergence standard deviation is much smaller than the surface relative vorticity standard deviation, is much smaller signature. In fact, as you go towards geostrophic motions, this goes down to 0. And so if we know that this is less than the relative vorticity standard deviation, then knowing that the correlation coefficients are basically the same, we can predict that the coupling coefficients will be smaller for the relative vorticity than for the divergence, for the wind stress divergence. And the same holds for the winds. And in fact, for the scales that we're taking a look at, this ratio is about a factor of 2. And so that explains this factor of 2 scale, just to a good approximation. So on the left-hand side is the observed coupling coefficients, and on the right-hand side is the coupling coefficients that you would predict just knowing the correlation coefficient and knowing the standard deviations of the various quantities. And so it says that if you want to know the correlation coefficient, if you want to know the coupling coefficient between the atmosphere and the ocean, basically you take a look at these correlation coefficients and then just multiply them by the relative ratios of the divergences. And you get a very good explanation of these coupling coefficients. Now I want to transition a little bit in the next 10 minutes to give you an example of a case study, a very interesting case that we have of atmosphere force in the ocean. And so we have wind roll conditions, fairly high wind speeds, wind direction from the top. And what you see in the top is the wind. This is the wind curl, and this is the wind divergence. And you can see the clear signatures of the rolls in here. And then what you can see in the currents, which we were all very surprised to find, is that you see very similar signatures in the currents. Now, the Doppler measures the currents at the very top of the ocean. So one of the things that we're working on is to find out how deep this coupling goes. But we wanted to characterize the coupling for this event to see how the ocean reacted over time, because this event lasted basically for 5 days. So I'm going to show you 3 days of this event. So one of the ways to take a look at is to take a look at the cross correlation of the curl between the wind as a function of angle relative to the wind direction. So 0 is the wind direction, and then we're having the cross correlation between the surface curl as a function of distance. And what you see is the clear indication in the cross track direction, but not exactly at right angles of the wind rolls. This is in the curl, and this is in divergence. At the same time, you see the same cross correlation in the surface currents. So you see that the signatures are similar, and that you have cross correlation in the direction at 90 degrees to the wind direction due to the wind rolls, but it's not exactly the same. This is tilted at an angle. In the divergence, this is pretty much at right angles to the wind direction, as is in the surface currents. Now we're going to take a look as the event developed, and this was taken at 8 o'clock in the morning, and we came back later on at 2 o'clock in the afternoon, and you can see that just between that time and this time, the wind rolls had strengthened and became much more clearly defined, and they're also much more clearly defined in the currents. Now you can see them clearly in the divergence as well. If you take a look at the cross correlations, now you have beautiful signatures both in the winds for the curl and the divergence. In divergence, again, clear signature in the cross-track direction, and you can see here the scale of those oscillations is in the order of 4 kilometers. And then you have on the currents, you have something which is, again, not tilted quite the same way. It has roughly the same signature, but it has much broader distribution of the rolls. So instead of being at 4 kilometers or so. They're more like, it's 6 kilometers or so at this beginning stage. Then we came back the next day. The wind rolls are still there, but as you can see, they're not nearly as prominent in the currents. And when you take a look at the cross correlation, you can still see a clear signature in the cross correlation in the winds, although now the angle relative to the wind direction has tilted, as expected. But the interesting thing is that all that energy that was concentrated in these very well-defined bands in the surface currents, just a day later has spread out in energy, even though we still have modulation in the cross-track direction, both in the curl and the divergence. So one of the things that we're speculating is that these wind rolls are forcing probably internal waves or something similar that are propagating. And right now, I'm taking a look at the dispersion relationship for these things, but I don't have time to show you those results yet. But this is quite interesting. But one of the things that it shows is the relative influence of the wind spectra on the current spectra. And so taking a look at a wider distribution of wind conditions and current conditions, this is over an entire almost 30-day set of conditions during what we call IOP2. What you have on the right-hand side is the 2D wind spectra, and on the right-hand side, the current spectra. And there are differences between them, but there is significant similarities between them as well. Specifically, you can see that when the wind spectra are highly directed, the current spectra are also highly directed, even though they're not exactly the same. So these are the wind roll cases, whereas where the wind spectra are more uniformly spread out, such in the cases where you have cells or filaments, the same thing happens in the currents, although there's not an exact correlation between the two of them. There's a very clear indication that there's at these very high spatial resolutions, influence of the wind spectrum and the current spectrum, and vice versa. Another way to take a look at that is to take a look at the directionality of the spectrum. So basically integrating the direction out in here in these spectra and seeing which are the dominant directions. And you can see for the same set of circumstances, basically when you have peaks, when you have the wind rolls in the spectra, you also tend to have peaks which are not nearly as pronounced in the currents, but you do have peak per peak. Whereas when you spread out in the winds, you're spread out in the currents as well. So it's not an exact correlation. There's certainly a spreading of energy and a decrease in the directionality, but it's also it's really a remarkable set of coincidences. One of the things that you can take a look at is the cross-spectral density between atmospheric rolls and filaments, and you can see in the cases where you have atmospheric rolls, in cases like this, both the along track and the cross track components of the wind are cross-correlated with the currents, whereas when you have the roll situations in this red, it's only the cross-track modulation that you can observe. The other thing that I wanted to point out is that you can see these wind effects if you take a look at the spectra of the surface currents. So depending whether you have atmospheric rolls, filaments, non-atmospheric rolls, or all the data, you get significantly different sub-mesoscale spectra. And so if you take a look at all the data, you have these thing that puzzled us for a very long time, which was something like a k to the -2 spectrum, which you would expect if you have something like internal waves or other sub-mesoscale motions flattening out to something like k to the -1. And where you can see that is when you have more normal conditions, that doesn't happen. It's just a flattening out of the spectrum. And this bump here occurs due to the atmospheric rules, due to the increase in energy at energies comparable to the atmospheric rules. So just let me make a quick summary of what we've seen. We have high-resolution measurements validated the previously obtained ranges of the vorticity to wind stress curl coupling coefficients. On the other hand, the divergence to wind stress curl divergence was a factor of 2, larger than expected, but if you just assume the same coupling coefficient. The vorticity to wind vorticity coupling, it can be positive or negative, and generally increases with decreased resolution. So the longer your scales, the more likely you are to have the same sign of eddies in the atmosphere overlying the ocean. But it is not always greater than 0, and the coupling can be significantly lower than the wind stress coupling. Both for vorticity and divergence, the best you can explain phenomenologically the signs and the relative strengths of the coupling by taking a look at the correlation coefficient between vorticity and divergence that doesn't change very much, and scaling by the relative strength of the vorticity and divergence signatures. At high resolutions, winds and current are tightly coupled, and they show similar 2D spectral characteristics, both in angular spreads and spectral breaks. And the atmospheric rolls and filaments couple winds and currents in different ways. When you have the roll situation, which is the case that I showed you, we have wind driven, you have a case where we speculate the wind rolls are exciting internal waves in the ocean, and that energy is propagating out. Whereas in the very low wind speed cases, where you have high surface currents and very low winds, you have opposite modulation, as you can see in cases like this one, where you have a clear overlying of positive vorticity, overlying negative wind stress curl. And so with that, I'll hopefully left some time for questions, and happy to take them and answer them now or later if you feel like emailing me and asking for more information. Thank you.
Thank you, Ernesto. Let's all give Ernesto a big round of virtual applauses. And please, if you have questions, just raise your hand, or you can also write them on the chat. Roger, please go ahead.
Thanks, Ernesto. Really interesting talk, a lot of material. Yeah, am I correct? At least look quite familiar to me. So I think these are the winds calibrated to the 4-meter Doppler measurements for the most part. Is that right?
You're right, Roger. Is one of the things that I highlighted over here is that in order to train the Doppler scattered winds, we had to use the best information that we had at the time, and the best information that we had at the time was from ADCP data. We now have information from something called Doppler, which is an instrument from Scripps that is able to get a training data set for the top currents and also as a function of depth. And I'm now redoing this exercise. And I didn't have time to show you the results, but I can show them to you all offline, Rogers, as a function of depth. And it's actually quite interesting. But it's expected that the coupling will decrease as you go deeper. And also, as you go shallower, there will be coupling due to things like wind drift currents that Roger has studied a lot. So I'll leave that for our future talk, I hope.
Thanks, Ernesto. I'll look forward to seeing that. I guess I was going to ask, so maybe this goes too far, but the question of what that wind drift is and what the profile is pretty open still, I think. But there's a possibility that at 4 meters, there is still something like a 1% of wind speed wind drift velocity. And it seems as though, in principle, that could influence the coupling coefficient calculation. And I just wonder if you have thought about that at all, or
I
if you
have,
rule
and
it out.
I don't know. We have no. In fact, there's a strong shear in the signature from the DOPVIS data, and I don't know if we have Luc online or somebody from Scripps, but they are reprocessing all the data. I've gotten some very preliminary data from them for some of these data sets, but the entire data set is still yet to be processed. But very interesting results, and I look forward to seeing the entire data set and sharing with you.
Yeah,
But
I'm
there's a
here.
strong shear.
I'm
Yeah.
here, and I agree, strong shear, and we see Stokes drift as well. And that's why, I'm curious to see, I mean, the way Doppler scat is calibrated with 4 meter ADCP data, this is the best you could do at the time, obviously. But I think we have to be a little careful in interpreting some of those currents.
And just last week or a few days ago, or it was yesterday, the full ADCP data was delivered. And so I'm in the process of retraining everything.
Yeah.
So Luc, if you feel the energy to reprocess even some more, it'll be great.
Yeah, I mean, we're pushing through all the data sets, but as you mentioned, the things that is transparent from the DOPVIS data is it enables you to get those, this profile from roughly 30 centimeters to 2.5 meter water depth below the surface, is that there is significant amount of shear, a lot of structure, in addition to the Stokes drift.
Yeah, but the shear structure also changes significantly from day to day.
Yeah. So that's why it's not trivial, and it's very much a research topic. And combining all those observational tools, will be very useful, and especially in better understanding what are the depths Doppler scat is actually capturing, which is still a question mark, I think.
Correct.
Please go ahead, Dudley.
I think Dudley had a question.
Yeah, he's muted though.
Okay. Hi, Ernesto, great presentation. I really, really enjoy seeing stuff coming out of Doppler scat. I hesitate to make this comment because I don't have a solution to it, but these correlations in a number of cases are pretty small. And I think it would be, it's important to try to figure out the statistical significance of those before pushing too far in the interpretation. And that's the reason I don't have a solution, is that that's critically dependent on the degrees of freedom, or the effective degrees of freedom in the observations. And, given the nature of these things like these atmospheric rolls and stuff, not all the grid points are going to be statistically uncorrelated. So the degrees of freedom is going to be less than the number of grid points that you have in there.
Absolutely. And I've tried to take that into account, Dudley, and I was hoping somebody would ask that, because if you look really closely there, in each of these symbols is the standard error after I've taken out the number of degrees of freedom, and I've assumed that I don't have not every point is independent, but I've assumed that depending on the level of smoothing that I'm doing in the data, you get different degrees of freedom. So these are the error bars for 1 kilometer data, given the fact that we have independent measurements for the currents at 200 meters. And then, so I guess I don't have them here, but these are the propagated error bars for the coupling coefficient in there. And I forgot to put in here the same coupling coefficient, correlation coefficients for different scales. But in fact, these error bars, as you mentioned, do grow significantly. And in fact, you can see the scatter grows significantly in there as well, due to the fact that we have fewer and fewer degrees of freedom. So I think formally, at least some of these things have error bars in there. How much to trust them, but it seems to me that the scatter is more due to differences in stability conditions and different in ocean conditions than numbers of degrees of freedom. There's an awful lot of data points going in here.
Okay, so I have one other comment if there's time. Way back when we first looked at this coupling in the tropics paper, it was in the Journal of Climate in 2001. We also found that the divergence coupling coefficient was like a factor of 2 bigger than the curl coefficient. And we speculated at that time that it was because of surface current effects that would affect the curl and the vorticity in the ocean and the atmosphere, whereas there was very little divergence in the ocean, so there wouldn't be much, and not much coupling. But that doesn't appear to be right based on your analysis, because you've taken into account the relative wind and things, and it doesn't seem that the currents are the explanation. I think if I understood right, your explanation is just the ratio of the standard deviations of the two fields.
Yeah,
and
that's correct.
You think a bit more about that, because that doesn't really surprise me, but I don't know what it means. You seem to understand.
Yeah, no, the dynamical explanation of why the two are so Gaussian and the correlation scales like that, you would expect that the correlation coefficient would not necessarily be like this. The magnitude of the correlation coefficient being very similar for the curl and the divergence at these scales is very surprising to me.
Yeah, but it's not really surprising that that it works that way, the ratio of the standard deviations. But I'm not sure that I really understand the significance of that point.
Yeah, so the significance is that it's not a dynamic difference; it's just a kinematic difference. When you take a look at derivatives and you try to look at the cross correlation of these PDFs, the conditional distributions are dependent on the relative standard deviations through this formula.
So yeah, if you look at those equations, I think so tell me if I got this right. If the divergence in the ocean is very, very small compared to the divergence in the atmosphere, that's what gives you the bigger coupling coefficient for divergence.
Exactly.
Yeah. And one of your other slides showed really nicely how strong the divergence in the atmosphere is when you get to those small scales. And the ocean's never going to do that. So the ocean divergence it's not surprising the ocean divergence is so weak.
Yeah, although it's a lot stronger at the submeso scales, and certainly once you start reducing. Yeah.
Anyway, very nice. Thank you. I'll probably have some other questions I'll send you by email.
Excellent. Thank you.
All right, we're getting close to the top of the hour. If someone has Marcos, if you have a quick question, we'll have time for that.
Yeah, I hope it's a quick question. So going back to the current measurements, so you said it's calibrated with 4-meter depth currents, but the measurement, of course, is it's a surface measurement. We don't know, the ocean motion effect, whether it belongs to 4 meters or any other depth. But that to go to get to the current, you actually need to remove from the Doppler the wind wave bias or the wave bias effect. So my question is, how much of this effect can actually impact your correlations here? Because if you don't remove this wind wave bias, then it means that some of that signal really will go into your current estimates, right?
Yeah, no, it's an excellent question, Marcos, and in fact, we've spent the first 3 years of this ESMO campaign trying to validate the measurements. And we've compared against ADCPs, we've compared against surface drifters, we compare against the Doppler instrument. And what we see is that independent of what the wind signature is, we're not seeing wind effects coupling into the current effects. Sometimes, like in the wind rolls, there's a clear signature between the two of them, but sometimes the winds are completely independent of the currents. And in that case, we still see good correlation between our estimated currents and the truth currents. But this is hopefully you'll be at the OVWST meeting, and I'll be able to talk to you about these things in person and show you some real data. I think we have negative time right now.
Sure. I'll be happy to discuss with you. Thank you.
All right, let's thank Ernesto again for a wonderful talk, and I'll see all of you next week, I hope. Have a good day.
Okay. Bye, everybody, and thank you.